infinite complexity. What of my chances to predict the throw of the dice that sit next to me? Laplace would have said that provided I can know the dimensions of the dice, the distribution of the atoms, the speed at which it is launched, its relationship to its surrounding environment. Theoretically, the calculation of its resting point is possible. The discovery of Poincaré and those who followed have revealed that just a few decimal places could be the difference between the dice landing on a 6 or 2. The dice is designed to have only 6 different outcomes, yet the input data ranges over a potentially continuous spectrum of values. So, there are clearly going to be points where a very small change will flip the dice from landing on a 6 to a 2. But what is the nature of those transitions? Computer models can produce very good visual representations that gives me a handle on the sensitivity of various systems to the starting conditions. Next to my Vegas dice, I've got a classic desktop toy that I can play with for hours. It consists of a metal pendulum that is attracted to 3 magnets, colored white, black, and gray. Analysis of the dynamics of this toy has led to a picture that captures the ultimate outcome of the pendulum as it starts over each point in the square base of the toy. Sure. Okay. Color a point white. If starting the pendulum at this point result in it ending at the white magnet. Similarly, color the point gray or black if the ultimate destination is gray or black. This is a picture you get. Wow, please look at the diagram picture. Wow, it's so marvel, right? It's like a punch. As in the case of population dynamics, there are regions which are entirely predictable. Start to close the magnet and the pendulum will just be attracted to that magnet. But towards the edge of the picture, I find myself in far less predictable terrain. Indeed, the picture is now an example of a fractal. Yes, this is a fractal, right? So Panji is a fractal. There are regions where there isn't simple transitions from black to white. If I keep zooming in, the picture never becomes just a region filled with one color. There is a complexity at all scales. A one-dimensional example of such a picture can be cooked up as follows. Draw a line of unit length and begins by coloring one half black and the other white. Then take half the line from the point 0.25 to 0.75 and flip it over. Now take the half in between that and flip it over again. If we keep doing this to infinity, then the predicted behavior around the point at 0.5 is extremely sensitive to small changes. There is no region containing the point 0.5 which has a single color. There is a more elaborate version of this picture. Start again with the line of a unit length. Now rub out the middle third of the line. You are left with 2 black lines with a white space in between. Now rub out the middle third of each of the 2 black lines. Now we have a black line of length 1/9, a white line of length 1/9, a black line of length 1/9, then the white line of the length 1/3. That was rubbed out on the first round, and then a repeat of the black, white, black. Please look at the diagram next. Well, you may have guessed what I'm going to do next. Each time rub out the middle third of the all black lines that you see. Do this to infinity. The resulting picture is called Cantor set, after the German mathematicians George Cantor, whom we will encounter in the last edge when I explore what we can know about infinity. Suppose this control set was actually controlling the outcome of the pendulum in my desktop toy. If I move the pendulum along this line, I find that this picture predicts some very complicated behavior in some regions. A rather strange calculation shows that the total length of the line that has been rubbed out is 1. But there are still black points left inside. 1/4 is a point that is never rubbed out, as is 3/10. These black points, however, are not isolated. Take any region around the black points and you will always have infinitely many blacks and white points inside the region. What do the dynamics of my dice look like? Are they fractal and hence beyond my knowledge? My initial guesses was that the dice would be chaotic. However, recent research has turned up a surprise. Wow, okay.